Hello dear students, welcome back to the lecture series on theory of semigroups with course code MMTE 405. So we were discussing Green's equivalences. So let's recall the previous lectures. We had defined L relation and R relation. Let S be a semigroup. So definition of L relation and R relation. Let S be a semigroup. S a given semigroup is a semigroup. Then we have defined a relation A. L relation is L related to B if and only if the principal left ideal generated by A is same as principal left ideal generated by B. And then we have defined R relation is R related to B if and only if the principal right ideal generated by A is same as the principal right ideal generated by B. Then we have seen that this A is R related to B if and only if there exists X, Y in S1 such that XA is equal to B and YB is equal to A. And also we have seen that A is R related to B if and only if there exists U, V in S1 such that AU is equal to B and BV is equal to A. So this we have seen in our previous lecture. Now today we will show that this L relation is right congruence and R relation is left congruence. That's what we have to see. So let's state this theorem. L is right congruence and R is left congruence. L is right congruence and R is left congruence. L is right congruence, R is left congruence. Proof. So this is L is an equivalence relation, R is an equivalence relation. So that's by definition actually, or you can easily verify these relations. They are equivalence relations actually. So let's prove it's L is right congruence. L is right congruence. So suppose A is L related to B, and let's choose any element. Let C belongs to S. C belongs to S. We had to show that AC is L related to BC. So this is true. A is L related to B. Then there exists X, Y in S1 such that XA is equal to B and YB is equal to A. So this gives let's multiplying right side by C. Both the equation is then we see that it's X AC is equal to BC and YBC is equal to AC, and this gives this AC it's L related to BC. So whenever A is L related to B and C belongs to S, then AC is L related to BC. So therefore L is a right congruence. L is a right congruence. So on similar way you can see that this relation R is a left congruence. Now we will see that these L and R relations, they commute. That's the next theorem. L and R, they commute, and the relation is L and R commute. That is, commute means L composition, R is same as R composition L. So we first show that this L composition R is subset of R composition and prove. So first we see this L composition R is subset of R composition L. Let's check this. So let's choose any pair in L composition R. Let A comma B belongs to L composition R. Then by definition of composition, there exists C in S such that A, C, they are L related, and C, B, they are R related by definition of composition of relations. Okay. So this implies from this you will see A, C is L, there exists X, Y in S1, and for this relation for C is R related to B, U belongs to S1 such that XA is equal to B and YB is equal to A, and since they are R related, it means that CU are related. CU is equal to B and BV is equal to C. So assume this A, B, they are in L composition R, so that means there exists C in S such that A and C they are L related and C and B they are R related. So by that proposition, since they are L related, therefore there exists X and Y in S1 such that XA is equal to B, YB is equal to A. Now this A, C, B, they are R related. So therefore there exists U and V in S1 such that CU is equal to B and BV is equal to C. Now let's define the following element. Let T is equal to, let's define this element. T is equal to, it's equal to YCU. It is in S because each element is in S. Then we see that then what's AU? You can see AU. It's equal to AU. What's A? A is equal to Y, B, or AU is equal to YCU. AU is equal to YC. Okay. A is equal to YB. Sorry, A is C related to L. It's here C actually, not. It's C here, sorry. Because A is C related to L, not B related to L. So now look at this. A is equal to YC. It's equal to YCU. That's equal to T. So AU is equal to T. AU is equal to T. And now dV is equal to A. It should be equal to A. What's T and V? dV. D is equal to YCU. D is equal to YCU. It's YCU V. YCU V. Okay. Now YC. What's YC? YC is A. Okay. YC. CU. CU is B. Okay, let's write CU. CU is equal to B. It's equal to YBV. YBV. Okay. DV is equal to YB. YBV, and BV is equal to C here. BV is equal to C, it's equal to YC, and YC is equal to E, and YC is equal to E. So let's first define this element, then we can calculate AU is equal to D and DV is equal to A. So it means that so this AU is equal to D. There is U, and V in S1 such that AU is equal to D. So that's AU is equal to D and DV is equal to A. So therefore A comma D, they are all related. They are all related. AD, they are all related. So now we see that DB, they are L related. D is L related to B. Then we will get A comma B belongs to our composition L. Okay, let's see that also we can see this YB B is equal to YB, it's YB is equal to CU, B is equal to CU, it's YCU, and that's equal to D. YB is equal to D. Okay, YB is equal to D. And now XD, what's XD? X into D, what's D? D is YCU. So XD should be equal to D. XD should be equal to B. So here CU is equal to B. So it will be YB, XYB, or you can see this CU, YC. Now let's look at this. YC is equal to A, and XA is equal to C, and CU is equal to B. Yes, it's equal to YC. What's YC? YC is equal to A, it's XA. YC is equal to A into U. Now what's XA? XA is C, it's C times U, and C times U is equal to B. C times U is equal to B. It's just a calculation. So that is we have this YB is equal to D and XD is equal to B. So this implies D, B, they are L related, because this X and Y, they are on left side, they are L related. So thus AD, it's this pair is R related, and this one DB is L related. Therefore AB, it belongs to R composition L. So whenever AB belongs to L composition R, it will also belong to R composition L. R composition L. So thus L composition R is subset of R composition L. So similarly we can see that R composition L is subset of L composition R. L composition R. So therefore L composition R is equal to R composition L. They commute. So these relations, they are equivalence relations, and they commute with each other. Now we have some other equivalences which are very important. So let's define this H relation. So H is actually, it's the intersection of these. It's L intersection R. So it's an equivalence relation. And we have one more relation, that's T relation, which they are joined. So it's actually meet, because the intersection is a meet actually, which is equal to join all these two.
And this join, because since L composition R is same as R composition L, then we have seen that in one of our previous lectures that this composition is this meet of the relations which commute with each other with respect to the composition. This meet is actually equal to the composition. This we have seen. So H relation, which is very important relation also, and this D relation, which is the join of these two relations L and R, it's equal to L composition R, as we have seen that this L composition R is same as R composition L. Then this join is equal to the composition, and this is the meet. H is the meet. It is the intersection of these two relations. So these are two more relations, H and T, where H is the meet of L and R, and D is the join of L and R relations. Okay. Now we define one more relation, that's called J relation. So for this, we first define the principal, two-sided principal ideal. Two-sided principal ideal. So let's first show this. Let S be a semigroup. Let S be a semigroup, and A is any element of S. Then show that. S1 which is this set, SAT such that S belongs to S1, T belongs to S1. Then show that this it's a subset of S. Obviously, it's a subset of S. Then show that this one is an ideal, two-sided ideal. Is two-sided ideal of S. It's two-sided ideal of S, and we call it two-sided principal ideal. Two-sided principal ideal generated by E. It's a two-sided principal ideal generated by E. And based on this two-sided ideal, we define another relation that we call the J relation. As in case of left principal ideal or right principal ideal, we had defined two relations L and R. Now we have two-sided ideal, we define another relation that we called the J relation. So let's define that relation. J relation. So now let's define this relation, J relation. Let S be a semigroup, S be a semigroup, and A comma B belongs to S. We say A is J related to B. J related to B is J related to P if and only if the principal two-sided ideal generated by A is same as the principal two-sided ideal generated by B. That's J relation. And it is an equivalence relation. You can easily verify it, and you can also see that that's as an exercise. You can easily verify this. Exercise show that A is J related to B if and only if there is four elements X, Y, U, V belongs to S1 such that this A, it is not a B, this B belongs to this set, it also belongs to this set, so B is equal to XAY and second, now A is here, so A must be equal to of this type U, B, Y. So this is an equivalence. This is an exercise for you. It's very simple. It's very simple. This one, and you can also see that show that L relation is subset of J relation, and R relation is subset of J relation. So it's again simple. It's again simple. And this L relation is subset of J relation, and R relation is also subset of J relation. So let's try to solve this one. Let A comma B belongs to L. So that means there exists X comma Y in S1 such that XA is equal to B and YB is equal to A. And this will give XA1 is equal to B and YB1 is equal to A. So that means there exists X, Y and 1 in S1 such that XA1 is equal to B and YB1 is equal to A. Now let's look at this. It satisfies this property. XAY is equal to B, XAY is equal to B, and YB. That's this. It's actually UBV here, not UBY. And UBV is equal to A. UBV is equal to A. So therefore, A comma B belongs to J. And on similar lines, we can see that this R is subset of G. R is subset of J. So both L relation and R relation, they are subsets of this J relation. They are subsets of J relation. So thus both L relation, it is subset of J relation, and R relation, it is also subset of J relation. So therefore L composition R, because it's the least equivalence, it's actually giant, as we have seen. That's the least upper bound of L and R, or the smallest relation containing L and R, smallest equivalence relation containing R. J is also an equivalence relation containing L and R, but L composition R is the smallest equivalence relation containing L and R. Therefore this must be subset of G. It is subset of G. So in other words, D is subset of G, because D is actually the least upper one. D is the joint actually. D is subset of G. D is subset of G relation. Okay, D is subset of G relation. So there are some examples where you can see the strict inclusion hold, but